Zeilberger from University of Birmingham. We will speak about the sequence calculus or a semi-associative law. As usual, for a speaker out of town, in this case out of this continent, we're going to take the speaker out for dinner at the usual place, 6:45. Everybody is welcome. If you're not going to use any electronic devices during the talk, and let me know right after the talk. You have to tell me, but everybody's welcome.
Okay, thank you very much. It's great to be here. Before I start the talk, or maybe I'll just give you a little bit of background. Well, to tell you that my background, I have a different background. I don't come from combinatorics. My background is more in logic and theory of programming languages. That's what I did my studies in. But for the last few years, I've gotten more interested in combinatorics. Kind of gone down a wild goose chase. And it started, like many wild goose chases, it started with the online encyclopedia of integer sequences. So, I'm that way. Hi everybody. Okay, so I was saying, just to introduce some context for my talk. I'm not from combinatorics, but I've been very interested for the last few years. Kind of gone down a wild goose chase. This is the experimental part of the talk, and like many wild goose chases, it started with the online encyclopedia. So here you have a few different sequences. My story started over here.
Can't laugh.
168.
Well, 168, sorry.
So one day, about 4 years ago, a little over 4 years ago, for some reason I decided to count some programs, computer programs in a very special language called the lambda calculus, and not arbitrary programs, but programs in some very well-behaved subset of lambda calculus. For some reason, got a sequence, counting the smallest programs. There's one of the smallest size, there's two of the next smallest size, then there were 9, then 54, and so on. And I entered it into the online encyclopedia and saw that, well, the first few entries at least seemed to match this sequence, number 168, which was already there. What was a bit mysterious is that it didn't say that it counted these programs, but that it counted something very different. And it counted various things, but it counted some family of planar maps. It turns out that this sequence was first computed in the 60s by the graph theorist Bill Tutte. And a planar map is just a graph embedded in the plane, and it turns out that this counts the rooted planar maps with n edges. Now, that was mysterious to me at the beginning. It turns out that in fact, there are a whole bunch of connections between lambda calculus and these maps. So a couple years earlier, independently, a group of combinatorists in France, so Olivier Bodini, Daniel Gardi, and Alice Jacot, they were counting another fragment of the lambda calculus, and they found that, well, it corresponded to another well-known sequence, this one, number 62980, which counts another family of maps, another family of graphs embedded in surfaces. So when you saw these two different sequences that both count different families of programs, different subsystems of lambda calculus, and they also count different families of maps, well, you might think maybe there's some larger pattern, and it turns out that there is, which is this cube. So all of these different sequences count different fragments of lambda calculus. So there's some logic to this cube. This is the largest This is the largest subsystem of programs, and then as you add properties, you get to the different corners of the cube. But these also count different families of maps. Now,
But initially they were counting only maps, or the application to lambda calculus also mentioned
no, well, all of them were counting different families of maps.
so the
All of them were known, other than one corner, this corner of the cube. And then we found out that they also count different subsystems of lambda.
So this new one with a big number
Yeah.
also counts maps,
Yes. Yeah.
and it's a new. They didn't know about it before.
No, it wasn't. Yeah. But okay, but so this talk is going to be at this, about this corner of the cube. So this also counts some family of maps, bridgeless planar maps, and it also counts some family of lambda terms. But it turns out that, in fact, it counts something else, and this was a discovery of Frédéric Chapoton about a little over a dozen years ago. He found that this sequence also counts intervals of the Tamari order. So what is this? What is the Tamari order? The Tamari order is this classic. It's a classic order relation. It was first studied by Tamari in the 50s. He introduced this, and it's a partial ordering on binary trees, where you order them by the rotation operation. So a rotation on binary trees takes a configuration like this, where you have a left-leaning tree, and it reconfigures it to a right-leaning tree. So this induces a partial order on all of the binary trees. Now, the original reason that Tamari was interested in this, you can think about this as a sort of directed version of associativity. So if you think of these as words, ways of multiplying three letters, so call them A, B, and C. So this corresponds to the left associated product, A times B times C, and this is the right associated product, A times B times C. So the Tamari order, so I'll just define it formally. The Tamari order it's the least relation. I'll write it A less than or equal to B on fully parenthesized words such that, well, it's of order, so it's reflexive, transitive, and now the product is monotone in each argument. So if A1 is less than or equal to A2, B1 is less than or equal to B2, then A1 times B1 is less than or equal to A2 times B2. And I'm going to write the product. Sometimes I'm going to write it like a times sign. Sometimes I'll write it parenthesized. And finally, you have this associativity law. So A times B times C is less than or equal to A times B times C. Okay, so that's the order. Now, Tamari, he originally introduced this. He was studying algebra. He was studying a classic problem in algebra of the when can you embed a semi-group into a group. And this was for his thesis. He studied from a pretty abstract perspective and introduced this order. But it turns out that this is a very interesting order. It has lots of interesting properties. So one very interesting property that Tamari noticed in his thesis is that if you take you take the binary trees of a given size. So take the binary trees with n vertices, right? There's a Catalan number of them. And then you arrange them by this order, which is the partial order on binary trees. And if you take the Hasse diagram of that partial order, it defines the skeleton of a n-1 dimensional polytope. So this is something you might have seen before. It's sometimes called the icosahedron. So here on the left, drawn the 5 different binary trees with 3 internal nodes and 4 leaves. And at the bottom, you have the left-leaning comb. At the top, you have the right-leaning comb. So this is at the bottom of this order, this is at the top. And well, you can get from the bottom to the top in different ways. So we can get from here to here by taking this vertex and rotating it to the left, to the right, sorry. And then we get from here to here by taking this vertex and rotating it to here. Or alternatively, we can take this vertex and rotate it to here. And then we take this vertex and rotate it to here. Then we take this vertex and rotate it to here and we get there. So, okay, so that's this, the 5 binary trees with 3 internal nodes form a 2-dimensional polytope, a pentagon. If you go to the next size, here's sort of a schematic picture of, well, there's 14 vertices here. I haven't filled in the binary trees, but I did that as an exercise for you. So this is the 3-dimensional icosahedron. You can go higher and higher. If you take the binary trees with n internal nodes, that defines an n-1 dimensional polytope. So that's kind of the amazing fact number 1 about the Tamari order.
And what polytope is that? 3-dimensional. It's the icosahedron.
It's the
And the bottom is bottom left, and the top is top right. The two at the root.
Yeah, this is. I mean, you can realize the polytope in different ways here. I mean, but it's composed of some 4-sided, some squares or rectangles, and some pentagons.
And the bottom right is the most leftist.
Yeah, this thing. And here you have this thing.
The right wing.
Yeah, and then going from this vertex is connected to 3 other vertices, and that corresponds to the 3 choices of nodes to rotate. So, if we rotate this to here, we get from here to here. I mean, it depends how exactly. I don't remember how it's oriented, but going to the different vertices corresponds to rotating the different nodes. And right, in this here, every vertex is connected to 3 other vertices because it has 4 internal nodes, and you can pick any one other than the root to rotate. Okay, so let me just write that out. So I'm going to call Yn. So Yn is the set of binary trees with n internal nodes. so n plus 1 leaves under the Tamari order. So partially ordered by this order, and so the amazing fact is that the Hasse diagram of Yn is an n-1 dimensional polygon. Now, another amazing fact. Well, this Yn, each of these posets Yn, it's not just a partial order, but it's actually a lattice.
And these amazing facts are due to Tamari?
So this amazing fact was claimed by Tamari in his thesis. He observed it, and then it was proved by, so observed by Tamari. It was proved by Friedman, Haya, Friedman, and Tamari. So they have a paper from 1967, but in another paper, Tamari says this was actually done in 1958, but then there was some, so it took them a long time to publish it. But, so let's say 50s, 60s. So, and by lattice, again, by a lattice I mean that for if you have any two binary trees, A and B, you can find some binary tree, call it A join B, such that you can get from A to A join B by rotations, and you can also get from B to A join B by rotations, and it's the least upper bound. So if there's any other C which is above A and B, then you can get from the A join B to C. Okay, so it has joins. It also has the dual property of meets. So there's some tree which is below A and B, and whenever C is below A and B, then it's below A join B. So there's the joins and the meets. It also has a least element. The least element is kind of, the fact that it has least on top, that's kind of clear. So that's this is the least element. This is the greatest element. The fact that it has this property, that it's a lattice, is not clear at all. And this proof was kind of complicated. I mean, they gave it kind of a long proof. Then there was a later paper by Wang and Tamari. So Haya, Friedman, and Samuel Wang were both students of Dr. Tamari. But this is also kind of complicated. There's actually a very nice video very nice talk by Don Knuth, which is online, you can find, called The Anatomy of Associativity, where he talks about this property of the lattice property of the Tamari order, and he gives a nice proof of it. I mean, so yeah, he gives a nice proof. It's a very nice lecture. But we'll get back to that. So that's the first amazing. That's the second amazing fact about the Tamari lattice. One more amazing fact. Well, so this is what Chapoton observed. So this thing, the fact that now, if you count intervals in the Tamari lattice Yn, so the number of intervals in Yn is equal to this formula, which is corresponding to the sequence, 2 times 4n plus 1 factorial over n plus 1 factorial times 3n plus 2 factorial. By an interval of the Tamari order, I mean a pair of binary trees that are related. So if you look at this one, so this is y3, this is y4. So if you look in y3, and you count, there's 13 intervals, because there's 5 intervals corresponding to each of the vertex. So each vertex, this tree is below itself, this tree is below itself. Then there's another this is below this, I think that's 5, so 1, 2, 3, 4, 5. Then there's this interval, and then there's this interval, and so there's 13 total intervals, which is given by this formula. Okay? So what's kind of amazing, well, Chapoton, he talks in his paper, Chapoton wrote a paper in 2006, where he mentions, basically the way that he arrived at this, well, he started counting intervals, entered it into the Encyclopedia of Integer Sequences, and got this formula. Okay, where did this formula come from? Actually, this is another formula that was computed by Tutte in the 60s for another family of planar maps. But Chapoton, once he saw this formula, he was able to prove that it does indeed count the intervals. Okay, so
I remember the Canadian Journal, right?
The Canadian Journal of Mathematics.
Yeah, lots of sequences.
Okay, so our goal today is going to be to explain 2 of these facts. Okay, so our goal is going to be explain amazing facts number 2 and number 3. But why is that our goal? So I just erased. So my original motivation for my original motivation actually was to try to understand. Well, I showed you that it turns out that there's these connections between lambda calculus and planar maps, also non-planar maps. It turns out then that there's also this connection between planar maps and the Tamari lattice. So this was something that Chapoton discovered again like 12 years ago, and some other people have actually tried to find bijective explanations of this. But now you might try to triangulate. Well, we have that lambda calculus is somehow related to planar maps. The Tamari lattices are somehow related to planar maps. Well, so maybe there's some kind of connection between lambda calculus and the Tamari lattices. So the idea for trying to better understand this connection was to look at the Tamari order as a logical system. As a deductive system. What do I mean by that? Well, lambda calculus is a programming language, but it also has many connections to logic. There's a sense in which you can see some programs of lambda calculus as proofs in formal logic. I'm going to explain how you can see the Tamari Tamari order that way, how that you can see intervals as kinds of proofs in a very, very primitive deductive system. Okay. So, people have any questions yet? Okay.
I have one question. Can you combine Y3 and Y4 and Y5? Is there one big, huge cluster diagram? That's a Tamari big picture?
So one thing here, is a consequence of these definitions that the only way that we'll ever be able to relate a pair of trees is if they have the same frontier of leaves.
Yeah.
So this order is really a disjoint union of lots of orders. So these things are not, at this level they're not connected.
Yeah.
Okay. So let's move over. Okay, so now I need to have one more bit of background, and I'm going to talk about this idea. So this idea of what is called sequent calculus. This is an idea, old idea in logic, that goes back to Jensen in the 1930s. It's a way of structuring a deductive system, like to do logic, and it's based on, well, it's called sequent calculus because it's based on the sequent. And what is a sequent? Well, it's something that looks like this. So you have a sequence of formulas, and you have an arrow, and then you have another formula. Okay, so it's just something that looks like this. You have a sequence of formulas, and you have another formula, and the idea is that you think of this as saying, well, so under hypotheses A1 through AN, the conclusion B holds. Okay. So this is just a logical statement. You can think of this, part of the motivation for this, well, if you take the case n equals 0, so this saying that B is true. If you take the case n equals 1, A, B, this is saying that A entails B. And so this notion of sequent is somehow generalizing these judgments that people make in logic to the n-ary case. And this turns out to be very useful. So we're going to do something like this, now for the Tamari order. So I'm going to introduce a sequent calculus, which is going to capture this order. So I think you're going to have to go.
Is the sequence ordered? Is A1, A2 the same as A2,
So yeah, it's A1. It's a list. A1. It's a list of formulas A1 through AN. Okay. So I'm going to write here now 4 rules that are going to define